All right, hello everyone. This is Bria, and today we'll be discussing and learning about Chapter 21, Optical Properties of Materials. I'll be touching on the first few topics in this chapter, however it's quite long, so we may not get to all of them today. To start, we'll go over the objectives. So, after a material is exposed to electromagnetic radiation, it can be useful to predict and alter its response. Chapter 21 will focus on how to understand properties and mechanisms of a material's optical behavior. Here are the outcomes: computing energy of a photon given its frequency and Planck's constant. Briefly describe the electronic polarization that results from electromagnetic radiation atomic interactions, and list off 2 consequences of electronic polarization. We also want to be able to explain why metallic materials are opaque to visible light. We want to be able to define the index of refraction, as well as describe the mechanism of photon absorption for A, high purity insulators and semiconductors, and B, insulators and semiconductors that contain electrically active defects. And for inherently transparent dielectric materials, we want to be able to note 3 sources of internal scattering that can lead to translucency and opacity. And lastly, we'd like to be able to briefly describe the construction and operation of ruby and semiconductor lasers. Moving on to the starting concepts, we're going to walk through filling in the blanks, typical Kyle Rogers lesson style here today. So, we have electromagnetic radiation, which is considered to be wave-like. We'll just fill this in as we go. And this type of radiation consists of electric and magnetic components, which are perpendicular to each other, as well as the propagation direction. We can see here a bit of an example, and to me, kind of looks like a sine wave, one may say. Yeah, so what we have here actually is an electromagnetic wave, which shows the electric field. So we'll highlight the corresponding variables. So we've got the electric field here, which is shown here. And then we've got the magnetic field. We'll go for some pink here, and then in purple, the wavelength. Yeah, and that's our graph. Those are the components of it. Moving on, we have several different types of electromagnetic radiation, which to me kind of sound a little familiar. We've got light, we've got heat, we've got radar, and we also have radio waves. And yeah, so we have a spectrum of electromagnetic radiation. Which spans from gamma rays that are emitted by radioactive materials all the way through X-rays, ultraviolet, infrared, and radio waves. So here is a diagram of this spectrum we're talking about, which includes the wavelength ranges for the various colors in the visible spectrum. So we can take a look on here. We can see over here the visible spectrum wavelength is highlighted. And yeah, you're kind of really told the ranges to look at for the typical RGB colors. We got red, orange, yellow, green, blue, and violet. Yeah, anyways, I think it's pretty neat. Moving on. All electromagnetic radiation moves through a vacuum at the same speed as light, which you could have guessed that one because I put the value right here. And this velocity, which we're going to be referring to as c, it's pretty important. It is related to the electric permittivity of a vacuum and the magnetic permeability of a vacuum, by this equation here. Let's do it in bright red. So we have the velocity, c, is going to be equal to 1 over the square root of the electric permittivity times by the magnetic permeability, mu naught. And there is our formula. So we got a couple other important equations to note. So we already covered that c is velocity, but it's important to note that we can actually represent c with the formula gamma times v. And as we've also talked about here, gamma represents wavelength. And what could v represent? Perhaps maybe frequency? And then we also have this other formula here. E, that's kind of new. H, it's also kind of new. Like, what are we talking about here? Come on, Bria, like, what? So E does represent energy. That kind of makes sense, I'd say. And H, that's a new constant, which I did mention at the very, very start. It's called Planck's constant. And I'd say that's a pretty important one for this unit. And so you do want to know the value of that, which it is 6.63 times 10 to the negative 34 joule seconds. All right. Give you a chance to write that down. All right. And now we're moving on to light interactions with solids. So, what happens when light moves from one medium to another? Some of the light might just transmit right through the medium, which, we'll talk about what that means down the bottom of the page, but I feel as though we all have a pretty good hypothesis as to what that's called. Next up, some light could be absorbed. As well as the light could be reflected at the interface between the media. And so we see this other equation here. We have I naught is equal to IT plus IA plus IR. So we're told here that I naught is the intensity of the beam incident to the surface of the solid. Now, what is IT, A, and R? Well, T, it's going to stand for transmitted. So the transmitted beam intensity, of course, and A will stand for absorbed, the absorbed beam intensity. and R is the reflected beam intensity. Now, back to what I was talking about at the start. We have materials that are capable of transmitting light with little to almost none, or almost no absorption, and those materials are called transparent, or, in more familiar terms, clear. Then we have materials where light can be transmitted diffusely, so some light might go through, but some light isn't going to be allowed to pass through. I like to think of this as like maybe parchment paper is a good one. If you shine a flashlight through it, you're going to get some light, but it's not going to be the full intensity of the light that you started with, because the parchment paper itself is going to absorb some of that light. So here we could say that the light is diffusely transmitted, and that material is referred to as being translucent. And then we have materials that don't allow any transmission of light that we can see, and those materials are called opaque. All right, we're going to move on now to optical properties of metals in particular. So we just talked about some general material terms and formulas. Now we're going to look at metals. So obviously that's a big part of this course. So here we have this diagram, this lovely diagram. We'll just take a look on it. We've got some new words: Fermi, energy, photon, absorbed. What are we talking about here? Well, this schematic representation is of the mechanism of photon absorption for metallic materials, where an electron is excited into a higher energy and an unoccupied state. So the change in energy of the electron, which we'll refer to as delta E, is going to be equal to the energy of the photon. And so that is the first side, schematic A, like right here. And then we have, I'm looking at B next, and B is the re-emission of a photon of light by the direct transition of an electron from a high to low energy state. So if you zoom out here, we can see that in the first one, the photon absorbed, we're looking at an absorbed photon, and in part B, we're looking at a emitted photon. So that's sort of the difference in these two diagrams here. Now, it's important to note that both the figures show a high energy band that is only partially filled with electrons. And metals themselves are going to be opaque, so that means they don't allow any light to pass through, as we just covered. And this is because of the incident radiation, which has frequencies within the visible range. And it excites electrons into these unoccupied energy states above the Fermi energy. So back to the diagram. See this line here? That is the Fermi energy line. And so the electrons get excited above it by however far, and that is our change in energy, or delta E. And it's also important to note that metals are opaque to all electromagnetic radiation. All right, so since metals are opaque and highly reflective, the perceived color is determined by the wavelength distribution of the radiation that is reflected and not that is absorbed. So we'll see a bright silvery appearance in metals when they are exposed to white light, and it indicates the metal as being highly reflected over the entire range of the visible spectrum. So I feel like that's just sort of a lot of fancy terms to say that, metal is reflective and metal is opaque. And when you look at metal, it typically looks silver because we usually look at it under white light. Moving on, we're going to talk about the optical properties of nonmetals, which are also just as important. So, light that is transmitted into the interior of transparent materials experiences a decrease in velocity, and as a result, it is bent at the interface. And this is called the process of refraction. So, we've got a pretty important ratio to talk about, and that is the index of refraction, which is the ratio of the velocity in a vacuum to the velocity in the medium. And again, it's called the index of refraction. All right, and so we got another formula here, woo! We've got N is equal to C over V. I'm going to make this a little bit bigger, a little bit bolder maybe. So N is the index of refraction, C is our velocity in a vacuum, and V is the velocity in a medium. There we go. So now we're going to look at the velocity of light in a medium in terms of the medium's electric permittivity and magnetic permeability. I had to type this one out, so I'll rewrite it. That makes it a little bit easier to see. But we have the velocity in a medium. It's going to be equal to 1 over the square root of the electric permittivity. Like that. And as we already talked about, we have the permittivity and permeability of a particular substance. So we can rearrange this first formula, N is equal to C over V. And we can see how the dielectric constants and the relative magnetic permeability can be used to solve the index of refraction. All right. Next up, we have this lovely indice of refractive indices, I guess, for certain transparent materials. So, you look at these, we see some ceramics and some polymers, and you can see their average index of refraction. So, that can be pretty helpful when, I guess, determining how transparent something is and whatnot. Anyways, if you want to learn more about that, you can check out table 21.1 in your textbook. But moving on, we have when light radiation passes from one medium into another, which has a different index of refraction, some of the light will be scattered at the interface between the two media, even if they are both transparent. And it is reflectivity that represents the fraction of the incident light that is reflected at the interface. Reflectivity is our word here. And we have this formula here where R is equal to IR over I naught. And we've got R representing reflectivity, as we just discussed. IR is the intensity of the reflected beam, and I naught is the intensity of the incident beam. Now, we got a special case here where if light is normal or perpendicular to the interface, then we see this formula here, where we got the reflectivity is equal to N2 minus N1 over N2 plus N1 all squared. And N1 and N2 are the indices of refraction of the media. And lastly here we have non-metallic materials may be opaque or transparent to visible light. If transparent, they often appear. I'll let you have a guess at that one. Yeah, so these non-metallic materials will often appear colored if they are transparent. Let's write this in bright blue here. Yeah, we got a couple more schematics to look at. So, in the first eye on the left, diagram A, it says that the mechanism of a photon absorption for non-metallic materials in which an electron is excited across the band gap, leaving behind a hole in the valence band. The energy of the photon absorbed is delta E, which is necessarily greater than the band gap energy. So this looks similar to the last diagram, except for instead of having our Fermi energy line, we have a band gap. So the electrons are moving further to cross the band gap once they get excited. And in diagram B, we see that the emission of a photon of light by a direct electron transition across the band gap. Then we have absorption of a photon of light may occur by the promotion or excitation of an electron from a nearly filled valence band across the, as we just talked about, across the band gap. And into an empty state within the conduction band. Ooh. And these excitations with the accompanying absorption can take place only if the photon energy is greater than that of the band gap. And we got another couple formulas here. Basically, just a formula to kind of summarize what that little paragraph says. We've got HV is going to be greater than the band gap, or in terms of wavelength, HC over gamma is equal or is greater than the band gap. And lastly, we'll do a quick example, sort of practice question style of what you might be seeing. So, the problem is saying that the fraction of a non-reflected light that is transmitted through a 200 millimeter thickness of glass is going to be 0.98. And they want us to calculate the absorption coefficient of this material. So I'll give you a second to try this problem, and then I'll go through my solution. All right, we're back. So the problem is asking us to solve for beta, and we have an equation that can get us there that we've seen in our textbook. This equation looks as such. All right, so do you think we have everything we need to solve here? Because to me, it looks like we do. So moving on, we will rearrange to solve for our missing variable, and then we'll plug in the numbers, and that'll hopefully give us the correct answer. So if you already tried it, you probably already know, but I'm just going to do a little quick algebra to rearrange this equation. It's going to look like this. Oh, but beta is still not by itself, so we're going to do one more step there. All right, that was a messy bracket. So now I think we can plug in our values. So personally, I'm just going to leave this in millimeters, but if you wanted to take the 200 millimeters and change it to 0.2 meters, then that's fine. You're just going to have to adjust the units of your final answer. The units of my final answer are going to be 1 over millimeters, but you could just have it as 1 over meters if that was what suits your question better, you know, in the context of using this example. Or if you just prefer to work in meters, then that's all good. However, if you check out the textbook and look at this specific example, they are also going to leave it in millimeters. So let's see what that would look like. Now, one important thing to note here is I'm putting in 0.98 as this fraction. And that is because we are told that the fraction is equal to 0.98. We're not told our transmitted and regular intensity. We're just given the fraction. You could be told these two separate values right here and here, but in this case, we're just given a fraction, so you just can plug that right in. And if you chuck that into your calculator, you should get that beta will be equal to 1.01 times 10 to the negative 4 millimeters to the negative 1, just like that. And there's our final answer. And that also concludes today's lesson. Thanks for following along. Hope you have a great night.